In this video lecture, I will extend the concept of equivalent resistance already discussed in the specific case of resistors in parallel and in series. I will then introduce Thevenin and Norton theorems, which are quite important for simplification and modeling of electronic circuits. Let us consider a network including a set of resistors connected together in various ways. Suppose that the network is inside a box, so we don't actually know how the resistors are connected together. Suppose now that we want to find the equivalent resistance for this network. Actually, there is not just one single equivalent resistance for a given network. In order to define the equivalent resistance, together with the network, we also need to provide a pair of nodes in that network. The equivalent resistance is always defined between two nodes of a given network. So let's choose, for example, node A and node B in the network inside the yellow box. Let's expose now the two nodes A and B in such a way that they stick out of the yellow box. The symbol we use to represent the equivalent resistance between the nodes A and B of the network is this one, where R sub EQ is the name we give to the equivalent resistance. Saying that the resistance REQ is the equivalent resistance seen between nodes A and B of the network means the following thing. Let's apply a voltage source Vp between the terminals A and B of the network. The network will draw some current Ip from the voltage source. If we apply the same voltage source to the resistor R sub EQ, and this resistor is equivalent to the network between nodes A and B, then this resistor will draw exactly the same current Ip as the network under investigation. Note that if we put the equivalent resistor Req also inside the box, then we couldn't tell the difference between the network we started from and the equivalent resistor. Actually, the two networks behaves in exactly the same way when we apply a voltage source Vp to the two exposed terminals. As I said, the equivalent resistance is defined when we specify the pair of nodes of the network between which we want to calculate it. If only one node is indicated explicitly, then it is assumed that the other node is the ground reference. The definition we gave for the equivalent resistance provides us with an operational method to calculate it or even to measure it. So let us consider the same network as before, and let's apply the same voltage source Vp between nodes A and B of the network. Let us assume that the network draws, as before, a current Ip from the voltage source. Then, if Req is the equivalent resistance for the network between nodes A and B, then Req is given by Vp divided by Ip. This is what we get by applying Ohm's law to the network, including the equivalent resistor Req, where Vp and Ip are the same by definition as Vp and Ip in the original network. By the way, the subscript P in Vp and Ip stands for probe or probing. The same purpose can be served by using, instead of a probing voltage source Vp, a current source Ip and evaluating the voltage Vp developing across the current source. The equivalent resistance will be again given by the ratio between Vp and Ip. Apart from using the just discussed operational method, the equivalent resistance of a network between two nodes can also be calculated by inspection of the network itself. So consider again the same network as before, and suppose you want to compute the equivalent resistance seen between the two nodes A and B. In order to make it easier to recognize the parallel and series connection between resistors, let us draw the same circuit again in a different way. Note that the topology of the circuit, which means the way the resistors are connected to each other, is the same for the two circuits. So the equivalent resistance seen between nodes A and B in the circuit on the left or in the circuit on the right is the same. Note that R1 and R3 are in series, so they can be replaced by an equivalent resistor with a resistance which is the sum of R1 and R3. This resistor is in parallel with R2, so we can replace these two resistors with a single one given by the parallel between the two, so R1 plus R3 in parallel with R2. Also, R5 and R6 are in series, so we can replace them with an equivalent resistor given by R5 plus R6. Then we observe that this resistor is in parallel with R4, so we can replace the two resistors with an equivalent resistor given by the parallel between the two, so R5 plus R6 in parallel with R4. Note now that the two remaining resistors are in series, so eventually the equivalent resistance can be written as R1 plus R3 parallel R2 plus R5 plus R6 parallel R4. Note that if we change the nodes between which we want to calculate the equivalent resistance, the equivalent resistance is going to change. Let us consider the same network as before, and let us calculate the equivalent resistance seen between node A, which is, as before, the node between resistors R1 and R2, and node B, which this time is the node between resistors R5 and R6. This network has the same topology as this other network. The equivalent resistance can be easily calculated as R1 plus R3 in parallel with R2 plus R4 plus R6 in parallel with R5. Now compare this result with the one obtained before with a different choice of the node pair A and B. Consider now an electronic circuit including not only resistors but also independent current and voltage sources. Suppose we want to find the equivalent resistance between nodes A and B. In order to do that, we can proceed as we did before and apply a probe voltage source and evaluate the current IP drawn by the network. However, before doing that, in case the network includes independent current and voltage sources, we need to switch them off. Remember that when you switch a voltage source off, you get a short circuit, and when you switch a current source off, you get an open circuit. Having done that, you can then proceed to the evaluation of the equivalent resistance, which will again be given by Vp over Ip. The same procedure has to be followed if we want to calculate the equivalent resistance by inspection of the circuit. Suppose we are given a quite complex circuit including resistors and voltage and current sources. Suppose we are just interested in figuring out what the voltage would be across terminals A and B in the network and what amount of current would flow through a load resistor attached between these two terminals. We could apply Kirchhoff's laws, which would mean setting up quite a complicated system of equations and solving it. Luckily, Thevenin's theorem can make things much easier. By the way, the authors of the theorem was actually a French engineer, so his name should be more correctly pronounced Thevenin. Using Thevenin's theorem, if only two terminals are of interest, these two terminals can be extracted from the complex circuit and the rest of the circuit can be considered as a black box. Considering the rest of the network as a black box means that we are not so much interested in the specific configuration of the network as in the way the network affects whatever is attached between the two nodes. Thevenin's theorem states that any linear two-terminal network can be represented by a voltage source in series with a resistor. This means that once we have chosen the nodes of actual interest, the network can be simplified into a network including just a voltage source and a resistor. In the case of Thevenin theorem, the voltage source is called Thevenin voltage source, indicated with VTH typically, and the resistor is called the Thevenin resistor, indicated with RTH. Together, they form what is called the Thevenin equivalent circuit. Note that circuit terminals, or the terminals of the black box, might actually not be present in a circuit. For example, instead, you may want to find the current and voltage across a resistor that is already within a complex network. In this case, you must remove the resistor and create two terminals, making a new black box, and then find the Thevenin equivalent circuit. Of course, this equivalent circuit will be different from the previous one. After the Thevenin equivalent circuit is found, we simply place the resistor across the terminals of the Thevenin equivalent circuit, calculate the voltage across it, and calculate the current through it by applying Ohm's law. We will see a few examples later on. Thevenin's theorem tells us that given a linear network and chosen two nodes from that network, the behavior of the network between the two nodes can be reproduced by means of an equivalent circuit consisting of a voltage source in series with a resistance. The meaning of the word equivalent here is the following. Suppose that we can close both the starting circuit and the equivalent circuit inside the box in such a way that we can make the two terminals A and B stick out of the box for both circuits. All we can see of the two circuits are the two pairs of terminals sticking out of the two boxes, and all we can do to understand their properties is to perform some kind of operation on the two pairs of terminals. If the circuit on the right is equivalent to the circuit on the left, there is no way to tell the difference between the two circuits inside the two boxes. For example, we can attach a load RL between nodes A and B of the equivalent circuit, and we will detect a voltage VL across the resistor and a current IL flowing through the resistor. If we attach the same load between nodes A and B of the original network, we will see exactly the same voltage across the load and the same current flowing through the load. The great advantage of working with the equivalent circuit is that the equivalent circuit is much simpler than the starting network. This definition of equivalence between the two circuits actually provides us with a method to determine the value of VTH, the Thevenin voltage source, and RTH, the Thevenin resistor. In particular, if the two circuits are equivalent, then the open circuit voltage between terminals A and B, which is the voltage between the two terminals when no load is attached, we call it VOC, open circuit voltage, will be the same as the open circuit voltage between nodes A and B in the equivalent circuit. Now, if A and B are not connected together, there will be no current flowing through the circuit, and then there will be no voltage drop across RTH due to Ohm's law. So the open circuit voltage between A and B in the equivalent circuit will be simply the voltage from the Thevenin voltage source. This tells us that in order to find the value of the Thevenin voltage source, we need to measure or calculate the open circuit voltage between nodes A and B in the starting network. VOC can obviously be calculated if the configuration of the network and the values of the components of the network are known. Now, what about RTH, the Thevenin resistance? The concept of equivalence we have discussed before also implies that the short circuit current between nodes A and B is the same for both circuits. By short circuit current between nodes A and B, we mean the current flowing between the two nodes when they are connected with an ideal conductor or short circuited. Let's call ISC the short circuit current flowing between nodes A and B in the starting circuit. In the case of the equivalent circuit, the short circuit current between nodes A and B can be easily calculated through Ohm's law as VTH divided by RTH. Since the two networks are equivalent, we can write that VTH over RTH, the short circuit current in the equivalent circuit, is equal to ISC, the short circuit current in the starting circuit. From this equation, we get that the Thevenin resistance is given by the Thevenin voltage divided by the short circuit current in the starting circuit. So as in the case of the Thevenin voltage source, the Thevenin resistance can be determined once the short circuit current between nodes A and B in the starting network has been measured or calculated if the configuration of the network and the value of the components of the network are known. Actually, RTH can be calculated as the equivalent resistance of the network between nodes A and B. Consider this network including a battery and 3 resistors. We would like to find the Thevenin equivalent circuit between nodes A and B. First of all, let's find the voltage of the Thevenin voltage source. We know that the voltage VTH is equal to the voltage between node A and node B in open circuit conditions. Note that no current can flow through R3 because the resistor has a floating terminal. Therefore, the voltage between nodes A and B is the same as the voltage across resistor R2 because there is no voltage drop across R3. Actually, based on Kirchhoff's law for voltages, we can write that V2 minus V3 minus VAB is equal to 0. But V3 is 0. So from here we get VAB equal to V2. Note that the battery and resistors R1 and R2 make up a voltage divider. So we know that the voltage V2 across the resistor R2 can be found as E times R2 divided by R1 plus R2. And this is also VAB in open circuit conditions. Eventually, this is the VTH we were looking for. By replacing the values of E, R2, and R1 in the expression of VTH, we find that VTH is equal to 6 volts. Now, to find the value of the Thevenin resistance RTH, we need first to find the short circuit current between nodes A and B. Note that now, with the short circuit in place, resistors R2 and R3 are in parallel, so the voltage across R2 is the same as the voltage across R3. Let us compute the voltage across R2 and R3, which we call Vx. Vx here can be seen as the voltage at the output of a voltage divider consisting of the battery E and the resistor R1 in series with R2 and R3 in parallel. Therefore, Vx is equal to E times R2 parallel R3 divided by R1 plus R2 parallel R3. If we replace the values of E and of the resistors in this expression, we get 2 volts. Note that the short circuit current flowing between nodes A and B is the same as the current flowing through the resistor R3. Therefore, by Ohm's law, we can compute the short circuit current as Vx divided by R3. This gives 2 volts divided by 1 kilo ohm, or 2 milliamps. Eventually, RTH can be calculated as VTH divided by the short circuit current as per Thevenin theorem. This yields 6 volt divided by 2 milliamps, or 3 kilo. As I said before, the Thevenin resistance can be found also as the equivalent resistance between nodes A and B of the circuit. So let us find the equivalent resistance Req. We know that before calculating the equivalent resistance, if there are any voltage or current sources in the circuit, we need to switch them off. In this particular case, when the battery E is switched off, it will become a short circuit. Now, the circuit we see between nodes A and B consists of resistor R3 in series with resistor R1 which is in parallel with resistor R2. Therefore, the equivalent resistance by inspection of the circuit will be equal to R3 plus R1 parallel R2. If you do the math, you will find out that this yields 3 kilo ohm, which is exactly the same result we got before when calculating the short circuit current between nodes A and B. So again, RTH is equal to 3 kilo ohm. Find the Thevenin's equivalent circuit between nodes A and B for the three networks in this page. Norton's theorem is another tool for analyzing complex networks. Like Thevenin's theorem, it takes a complex network and replaces it with a simpler one. The only difference is that instead of having in the equivalent circuit a Thevenin voltage source in series with a Thevenin resistance, the Norton equivalent circuit consists of a current source in parallel with a resistance. This resistance happens to be the same as the Thevenin resistance. So Norton's theorem states that any linear two-terminal network can be represented by means of a current source in parallel with a resistor. The current source, I and O, is called the Norton current source, while the resistor, R and O, is called the Norton resistor. The equivalence between the two circuits has to be intended in the same way as for Thevenin's theorem. In particular, if the two circuits are equivalent, it will not be possible to tell the difference between the two just by performing current or voltage measurements between the two nodes A and B of the two circuits. In particular, if the two circuits are equivalent, then the short circuit current between nodes A and B in the starting network will be the same as the short circuit current between nodes A and B in the equivalent circuit. Again, by short circuit current between nodes A and B, we mean the current flowing between node A and node B when the two nodes are connected with an ideal conductor. In the case of the Norton equivalent circuit, the short circuit current between nodes A and B will be the current generated by the Norton current source. To verify that the short circuit current in the Norton equivalent circuit is exactly the current generated by the Norton current source, we can consider the equivalent circuit as a current divider where the resistor in parallel with R and O has zero resistance. So by applying the formula for the current divider, we get that the current flowing between nodes A and B, let's call it IAB, is given by the input current, INO in this case, times the resistance, RNO, divided by the sum of the resistances. So RNO plus 0, which makes exactly INO. Therefore, the current generated by the Norton current source, I and O, will be given by the short circuit current in the starting network. What about R and O, the Norton resistor? Note that in the Norton equivalent circuit, the open circuit voltage between nodes A and B is given by I and O times R and O, and this is obtained by Ohm's law. The voltage between nodes A and B is actually the voltage drop across the resistor R and O. Since the circuit on the left and the Norton circuit are equivalent to each other, then the open circuit voltage between nodes A and B in the starting network must be the same as the open circuit voltage between nodes A and B in the Norton equivalent circuit. So we can write that I and O times R and O is equal to VOC, from which we get that the Norton resistor, R and O, is equal to the open circuit voltage in the starting network between nodes A and B divided by the Norton current. As in the case of Thevenin's theorem, also for Norton's theorem, the Norton resistor can be found as the equivalent resistance between nodes A and B in the starting network. Find the Norton equivalent circuit between nodes A and B for the three networks in this page. Since any two-terminal linear network can be represented both through a Thevenin equivalent circuit and a Norton equivalent circuit, it should be possible to go from one equivalent representation to the other one, and it actually is. Note that if a Thevenin circuit is equivalent to a given two-terminal network and a Norton circuit is equivalent to the same two-terminal network, then the Thevenin circuit and the Norton circuit must be equivalent to each other. So the open circuit voltage between nodes A and B and the short circuit current between the same nodes must be the same for the two equivalent circuits. So suppose that we know the Norton current source and the Norton resistance, which means suppose that we have found the Norton equivalent circuit. By making the open circuit voltage in the two circuits equal, we get that VTH, the Thevenin voltage, is equal to I and O times R and O. As already said, the Thevenin resistance, RTH, will be equal to the Norton resistance, R and O. This can be easily verified by computing the equivalent resistance between nodes A and B in the two equivalent circuits. If instead the Thevenin equivalent circuit is known, then by making the short circuit current equal in the two circuits, we get that the Norton current I and O is equal to VTH over RTH, while the Norton resistance R and O will be equal to the Thevenin resistance.